All right. So what we're going to do today is I want to first of all show you in Canvas. I've set up for week 12, which is this week. I haven't really been doing much in Canvas recently, but I do want to show you what I've done so that you'll have access to many different resources. So just give me a second. Yeah. Let me share the screen. All right. So you should be able to see this, Faith. I see your picture there. You give me a thumb. You'd see it. Okay, good. That's somebody else coming in. All right. All right. So in this particular module, it should be available to you now. What you're seeing is actually my copy of it. So you're not going to see anything that's not checked here. All these other things that are not checked uh, are not available to you. But what I've given you, what I've given you is some videos from a past course that I taught using the same textbook. And I was actually, during the semester, I was out of the country for 2 weeks. So I pre-recorded these videos. So there's one for both, for section 6.1 confidence intervals, 6.2 confidence intervals, which I'll cover today. So these are complete lessons using the same text. So you can use those for review. And then a little further down, you'll see 6.1 hypothesis test, 6.2 hypothesis test. So I'm covering 6.2 this week, and but these 4 videos will be pretty much everything you need to know about how to do confidence intervals and hypothesis tests using formulas. In other words, we won't be dealing with STAT02260 at all when we're reviewing chapter 6. All the other sections of chapter 6 that deal with difference in proportions and difference in means, but we will not be covering those. In addition, and I might be referring to these during our today, but in addition, I've created these PDF documents which give a review of all the things that you need to know for confidence intervals. For example, there's confidence interval formulas. Also, the misinterpretations of confidence intervals. There's a PDF that's right out of the textbook. I actually have added an additional confidence interval misinterpretation. Sometimes in the final exam, there are questions regarding the misinterpretation of confidence intervals. So it's good to know these. So I printed them out so that you'll have easy access to them. All right, and then in terms of confidence intervals, I have basic facts about them in one PDF. I actually go over the 6 steps of hypothesis tests for proportions, and also 6 steps for hypothesis tests for means. That's that latter one we'll cover in class on Wednesday. And then I actually give you a couple sample hypothesis tests, one for a proportion and one for a mean in this PDF. So there's quite a few PDFs here, and also videos, the 4 videos. So there's a lot here that you can take advantage of. This is in addition to what the Wiley Plus has available also with their videos. So you should have plenty of resources to review. If what's covered in class you're not quite sure about, because I remember when I was a student and I went to class, I don't really remember much because I'm more of a visual person, so I need to see things and actually feel the paper and everything else I'm looking at. So I learn better not in the classroom, but better studying by myself. So for those of you who are like that, who don't, let's see, give me a second here. For those of you who are not feel like classroom setting is not the best time to learn things, but you do well in learning on your own, then these resources should help. All right, any questions about that? So this is all available in what's week 12 of Canvas. It's all should be available. And I checked it all of them open up, and all the videos are still good. The videos actually are, I made using Zoom and also recording them or copying them in YouTube. So they're available on YouTube, and I'm assuming they're there forever in YouTube. All right, just let me get all these people in here. All right, so the first thing we're going to do is I'll unshare this particular thing we're looking at here. And let me get to the textbook. Just give me a second. All right. All right, so this is section 6.2. You might have noticed that if you look at the textbook, that each 6.1 and 6.2 are divided into 3 sections. One that describes the sampling distribution. In 6.1, it's the sampling distribution, sample proportions. In 6.2, the sampling distribution of sample means. And then there's a section on confidence intervals and a section on hypothesis tests for each of 6.1 and 6.2. So there's 3 sections for each of the, I guess I shouldn't use section because the word sections used here, maybe 3 parts, we could say, 3 parts to each of the sections. Now, you're only responsible for 2 types of population parameters in terms of confidence intervals and hypothesis tests, and that is a population, you're estimating a population proportion, estimating a population mean, and that's it. That's it for that. There's no other parameters that we'll be looking at. We're not going to be looking at the difference in means, difference in proportions. We're not going to be looking at correlation coefficients. We're not going to be doing any of this stuff. Just looking at these 2 things. So there's a limited number of formulas that you'll need to know. All right. So some of these you may want to commit to memory just to make it easy for yourself, so you don't have to spend time thinking about it. In the when we're dealing with means, the standard error is this formula right here. It's the population standard deviation divided by the square root of the sample size. And that's it. That's all we need to know for the standard error when we're either doing a confidence interval or a hypothesis test for a mean. That's the formula. Now, the issue is that the population standard deviation, the numerator of this ratio here, is typically not known. You don't typically know what it is. So we typically have to estimate it. And the best way to estimate it is to use S, which is the sample standard deviation. So the sample that we get, whatever sample that we have, we'll calculate the mean and the sample mean, and we'll calculate the sample standard deviation. And the S is the sample standard deviation. So we're going to use that to estimate the population standard deviation. So this is an estimated standard error that we would use. All right, any questions about that? So that you know what we're doing. Okay, so we're just giving an example here of how to use it. And we're not going to use bootstrap or randomization. We're going to use the formula in this case here. All right, so let's look at example 610, part A. It says N, the sample size is 500. These are Atlanta commute times. And the average of the 500 participants in the survey is 29.11 minutes, and the standard deviation is 20.7 minutes. All right, so the standard error, let's just ignore the simulation part of it from STAT02260 because we won't be using it now. And if we just plug in those two numbers into the formula, so 20.7, the sample standard deviation is in the numerator, and the sample size, 500, goes inside the square root in the denominator. And if we use our calculator and divide these two, we get 0.93 as our standard error. Now, it's very important to remember that when you're dealing with a sampling distribution, this is the formula we're going to be using if it's a confidence interval, we're estimating a sample mean, or if it's a hypothesis test, we're going to be, we have a mean that we have a hypothesis test about. So the standard error will be using this particular formula. All right, so it's a simple formula. It looks a little bit simpler than the one we used in class for a proportion, that square root formula. This one only has a square root in the denominator. Okay, any questions about that? Now, when we replace the population, let's go back here, the population standard deviation with the sample standard deviation, then we end up with a different type of distribution. It's not a normal distribution anymore, even though it will look normal. It is called a T distribution. So when we come up with, for example, with a hypothesis test, if you remember last week, we came up with a Z statistic, right? It was like a Z score, where the denominator was the standard error, and the numerator was the sample proportion minus the hypothesized population proportion. All right, you remember we did that. In this particular case, because we're using the standard error as S divided by the square root of N, then the distribution we're going to be using is called the T distribution. All right, and so you're going to be sort of being introduced to it today. It looks pretty much looks like a standard normal, but it does change shape as the sample size gets bigger. And actually, once the sample size gets over 200 or 300, something like that, it sort of looks like a standard normal curve. But it has certain properties. And we're not going to worry about the properties of the T distribution too much. The only thing that we know is for a T distribution, the standard error is this formula, S divided by the square root of N. Now, as you remember, for a normal distribution, the only two things that we need to know to define what a normal distribution is the mean and the standard deviation. If you remember that, right? For example, test scores could have a mean of 100 and standard deviation of 10. And once we know that, we can draw the normal curve. So you only need to know two pieces of information for a normal curve. A T curve, which looks, again, a lot like a standard normal, only has one piece of information that you need to know. And I could go into this more formally if you wanted, but I don't think you will want to get into it too much. What you need to know is basically what's called degrees of freedom, or DF. And degrees of freedom for what we'll be dealing with in this particular course is strictly just one calculation. It is the sample size minus 1. Okay, so instead of going into what degrees of freedom is and the statistical, technical explanation of all of it, it's not that hard to understand, but I don't think it really helps you to understand it. Just know that when you use your calculator and you are going to be doing the t-distribution, instead of a mean and standard deviation that you're going to enter, the only thing you're going to enter is degrees of freedom. So if you know the sample size, you just subtract 1, and that is what you're going to enter into your calculator as degrees of freedom. And that's all you need to know for this course. All right. Any questions about that? Again, you'll see it when we actually use the calculator to do problems with this. Okay. It mentions here that for small sample sizes, the t-distribution sometimes doesn't work very well. However, in our course, 2 possibilities will exist. Either the population is normal, and if you remember, the central limit theorem says that if the population is normal, then the sampling distribution will be normal regardless of how big or small the sample size is. You don't have to worry about sample size at all. However, if the population is not normal, or if we don't know anything about the population, then it's good to know that the sample size of 30 or more is good enough. Now, this is true only for the dealing with the mean. All right, population mean or sampling distribution of sample means. It's only for the mean. We're not talking about proportions. If you remember last week, we had that special calculations that we had to do for proportions to check for normality. It was n times p, n times 1 minus p. If you remember, I went over that in class. That is just for proportions. The 30 or greater rule is strictly for a mean. All right. So that's what we're looking for. And just to make things simple, I mean, the book says 20 to 50 we could use, but to make things simple, and most statistics courses do this as an introduction, we strictly look at 30. If we have 30 or more in our sample, then we can assume that the sampling distribution will be normal. All right, we still need the random sample, but the second assumption is that it's normal if n is greater than 30, or n is greater than or equal to 30. All right, so that's what we're going to use in this course. This diagram here just shows different shapes for the t-distribution, how close it is to the normal distribution. You can read through it if you'd like. There's certain conditions that need to be met. All of these things, you can just skim through it. It's not that important. Okay, and there's some examples here of different distributions. They're really saying if the sample is extremely skewed or something like that, then you may not want to use the t-distribution. In this course, don't worry about it. We'll never have to give you a case like that. All right, either the population is normal or the sample looks pretty normal. So don't worry about it. When you have a confidence interval or hypothesis test for a mean, then we're going to use the t-distribution, and you're just checking to see if n is greater than or equal to 30. All right, that's all you're going to check for normality. You'll be fine. Okay. So that's it about the distribution. Now we'll practice actually, we'll do a few problems. We'll practice actually using our calculator for t-distribution. Actually, maybe we'll spend a little time now with this. Take a look at just so that you're familiar with it. Now, as you know, when using the normal distribution, there were 2 choices with our calculator. That was normal CDF. That's when we needed to find a probability, right? We had a value, and we needed to find a probability that is either less than or greater than that value, or maybe between two values. And it's the same thing, or if we were given an area or a probability, we were asked to find the particular value. And that was inverse normal. Now, it's the same thing with the t-distribution. There's a t-CDF, which is used for probabilities, and there's an inverse t used for finding the value that when you have the probability. Now, the problem could be if I know a couple of you have a TI-83 calculator, and anybody can unmute and tell me if you're here today. Are you here? Anybody with the TI-83?
Yeah, I have one.
Yeah, okay. Now, and the problem with the TI-83, and it's the only problem for this course, it's not a big deal, because I have a solution for it, is there's no inverse T listed in the TI-83. All right, that came with that was created for the TI-84 calculators way back when. So I do have a solution. There's a little program that's on my calculator, my personal calculator, and I'm able to transfer to your calculator. So please, those of you who have 83 calculators, bring them to class on Wednesday, and just I'll probably stop 5 minutes early, and just bring your calculators up, and I will transfer this program onto your calculator, and I'll show you how to use it. It's very simple. It's not going to be the same way that other people with the 84 calculators use inverse T. It's another function that you'll use on your calculator, but it works just as well. So make sure you have your calculator with you on Wednesday and come to class so I can update your calculator and so that you can use it when you get tested. All right. So that's all I have to say about that. So, but in terms of this, displaying what I'm going to show today, just bear with me for those of you who have the 83 with you today. Don't worry about it. Again, I will have this new program put on your calculator. But for now, just watch what I'm doing, and then everybody else will be able to do what I'm showing to you in class today. All right. So let's just take a look at some of the things that are here. Let's look at the skill builder section here. Maybe this might be helpful. All right. So you're given a random sample, and it says sample, let's look at 6.65, samples of size 1,000 from a population with a mean of 28, standard deviation of 5. Okay. And what you're being asked to find is the standard error for the distribution of sample means. All right. Now, actually, in this particular section here, it's easy to come up with the answer. Okay. Because you don't need inverse T or the T CDF. The only thing you're doing is dividing two numbers. So can somebody yell out, unmute yourself and yell out for 6.65? What would be the ratio that you would enter into your calculator to calculate the standard error? All right. So again, sample size 1,000, the mean is 28, and the standard deviation is 5. So this is from the population, so sigma is 5. We're using sigma and not x. So what would be, go ahead.
I was going to say, would it be 5 divided by the square root of 1,000?
That's right. Very good. Very good. Does anybody want me to display that using the calculator? Because it's pretty straightforward. But if yes, did somebody say yes? Did I hear that correctly? Somebody wants me to do that? Or no? I thought I heard somebody, but all right. So everybody's good with not showing that? All right. You all know how to do that. All right. All right, let's look at 6.67. What would be the answer for 6.667? Somebody else could yell out the standard error. What would it be? So we have a sample size of 40 from a population with mean 250, standard deviation of 80. So give me the ratio for the standard error. You don't have to calculate it, just tell me what two numbers are.
80 divided by the square root of 40.
Very good. Yes, that's it. All right. Is everybody good with this? I think you're all doing fine. That's it. And I just want to make sure that you know that's the standard error, not something else. All right. Now here's something a little bit different. Let's look at skill builder number 2. Now I'm going to have to show you how to do this first. We haven't really done this yet. 6.69 says find endpoints of a t-distribution with 5% beyond them in each tail if the sample size is 10. Now this is when you draw a t-distribution, draw it like it looks like a standard normal. Now I should let you know that a t-distribution has a mean of 0, just like a standard normal, but its standard deviation is actually bigger. It's not 1; it's something bigger than that. Okay, so when you make your drawing of the t, and I'll show again, I'll do this in class on Wednesday. Just draw what looks like a normal distribution, a bell-shaped curve, and just make sure that the middle value is 0. So what it's saying here is that each endpoint of the t-distribution, 5% is beyond them in each tail. So what does that mean? It means that 5% of the area is in the left tail, 5% of the area is in the right tail. So if that's true, what's the middle area? Just think of it, picture in your head what a bell-shaped curve would be. If 5% in the left tail, 5% in the right tail. Anybody might want to say what the middle?
90.
9. All right, so I'm going to actually write this down. So we have a t, 5% in each tail, and the sample size is 10. All right, so I'm going to unshare this and go to the calculator. Let's go to the calculator and share that. All right. So where do we find the t-distribution? We find it in the same place we found the normal distribution. And if you remember, we did the binomial. All of those probability distributions are in the same place. You click second distribution. Now, those of you who have the 84 calculator should look like this. Those of you who have the 83 calculator, what's missing is number 4, and that's the inverse t. Okay, so don't worry about it. Just follow along. And again, once I show you how to use your 83, it'll be very similar concept. So we're going to choose option number 4. That's what we're doing. We're doing an inverse t in this case here. Now notice it looks like an inverse normal with the exception that instead of having a mean and standard deviation, we have df, which is degrees of freedom. So again, if you draw what looks like a normal, but it's a t, or standard normal, and it has a mean of 0, and you draw some value of t on the left, some value of t on the right. One will be negative, one will be positive. The middle area is going to be 90%. If we want to find the positive value, right, the positive t that we're looking for, what area to the left would we put in? If the middle is 90% and each tail is 5%, what would be the area to the left of the positive t? What do you think?
95.
95, that's right, because it's the middle, 90, plus the left tail of 5. So I'm going to type in 0.95. Now, if the sample size is 10, what would be degrees of freedom? Remember this. The point. What is it? I'm sorry.
9.
9. Yeah.
9.
Yes. Yes. Good. So it's 10 minus 1. So for this particular course, degrees of freedom can get more complicated in future courses because it involves certain things that we haven't talked about. But for this course, we're keeping it simple. We're saying sample size minus 1. So if the sample size is 10, degrees of freedom is 9. And we hit enter where it says paste, and one more time. And that is your positive t. Now, if it's asking for 2 t's, one of them is going to be positive 1.833. Remember, I mentioned to you that if you're going to round at the end, always round with a minimum of 3 decimal places, unless you're being told otherwise. So it's 1.833, and the one on the left that's less than 0 would be negative 1.833, and those are the 2 t values. All right. Any questions about that? Does it make sense? Make sense? All right. All right. So let's unshare this. And let's go back to the text. So that's the answer. And by the way, in the electronic textbook, you can just click and it gives you the answer. And they rounded to 2 decimal places. I told you to round to 3. Please round to 3. All right. Because it's a different answer, right? 1.833 is, it's not the same thing as 1.83. So I don't like that answer totally, but that's what they put in there. All right, so let's look at some more. By the way, at 6.70, notice they have find the endpoints of a t-distribution with 1% beyond them in each tail. The sample size is 18. So if there's 1% in each tail, what would be the middle percentage? Well, 1% of the left tail, 1% of the right tail, that adds up to 2%. That leaves 98% in the middle. And so when we want to use the inverse t, we're going to have 98% in the middle plus the 1 on the left tail makes 99%. Okay? That's where we're going to enter area. And our degrees of freedom would be 17, 18 minus 1. All right? Any questions about that? And all the other ones here are pretty similar, except for 6.73. It says find the area in a t-distribution above 2.3 if the sample size is 6. So we should do that one. That's a little different because in this case, they give you a t value and you're being asked to find the area or the probability. In this case, above 2.3. So let's actually show you how to do it with your calculator. And by the way, TCDF exists for both the 83 and the 84 calculators. So that one you don't need to worry about. All right. So this again is again, second distribution. And we're going to scroll down this time to option number 6. Don't use option 5, use option 6, TCDF. It's the one you want. Now, those of you who have the 83, I'm assuming it's option 5, TCDF. Whatever it is, that's the one you want. Now, we do this exactly the same way as we did normal CDF, except we have degrees of freedom instead of a mean and standard deviation. So it's above 2.3. right tail. So that means the lower endpoint is going to be 2.3. And the upper, we're going to use some big number. It's recommended, if you want to do this, it's recommended to use the second and use EE, which is above the comma here. And you put 99 there, that's 10 to the 99th power, which is not much bigger than that. Degrees of freedom, we're going to use, let's say n is 6, we're going to use 5. And hit enter. Hit enter again. Now, for those of you who have the 83 calculator, you would have entered these three numbers with commas in between. And then it would look like this. Hit enter. And so the probability or area is 0.003 if you're going to round the 3 decimal points, 0.035 or 3.5% here. All right, so that's how you use TCDF, and it's pretty easy. I hope it's easy for you. Any questions? Everybody good with this? And hopefully you have your calculator and you're following along, but doing some game on your computer or something right now. But I hope you are following along, because otherwise you'll have to listen to this video again or watch some other videos to see these explanations. All right, so let's go back to the text. And let's move on. I think all of you are pretty good. Actually, maybe a word problem might be okay. I don't know. We could try one. No, I think we could skip these. These won't be ones that you'll see on the test. So let's just move on. Okay. Now I'm going to skip all these because I want to get to the actual confidence interval. There we go. So let's get to the confidence interval. Now, the math department has made a decision that for the most part, we're going to use the t-distribution whenever we estimate a population mean. All right, we're going to use the t-distribution as opposed to the normal. Now, is it possible that you may know the population standard deviation? If you happen to know it, you can certainly use z in the margin of error formula. Remember for when we were dealing with proportions, we use z times the standard error, which was the square root of p times 1 minus p over n, right? If you remember that formula. But if you are estimating a population mean instead of a population proportion, then most likely you do not know the population standard deviation, and you're going to replace sigma with s. And when you do that, then you can't use the z anymore, you use the t. All right, and that's where you need to use inverse t. All right, everybody clear on that? So that's basically what you're going to be doing for the most part. And so when you are given a word problem and being asked to estimate a population mean, which you're going to be doing a confidence interval, there's two things that you need to know. You need to know the sample mean, x bar, and you need to know the estimated standard error, which is s divided by the square root of n. And then once you have the standard error, you multiply it by the t using inverse t to give you the margin of error. And then you're doing the same thing we did before with proportions. We use the sample mean plus or minus the margin of error. That gives us our endpoints for the confidence interval. And we do it pretty much the same way as we did before. But we'll do some examples just to show you how to do it with your calculator. Now, once again, I'm showing you how to do confidence intervals using the margin of error method. There is an easier way of doing confidence intervals with your calculator using an actual function for it. I'm not teaching that yet. I want to teach this first because some of you may want to do this as opposed to using that other function because you don't want to make any mistakes in choosing the wrong function. So I'm going to show you this way first. You're going to use it this way. And if you happen to know the function and you want to use it, that's fine. But at this point, I'm not going to teach it until the very end. And then I'll show you what it is. And then as long as you feel comfortable with it and you're not going to choose the wrong one, then you certainly can use the other. All right, so there's your formula for confidence intervals when you're estimating a population mean. Okay, let's see if I can find a good example here. Well, I guess we could do this one here. This would be fine. This problem has to do with a particular United Airlines flight that goes from Boston to San Francisco. Who knows if this flight actually exists? And this was before the pandemic, during 2019. It was scheduled to leave each day around 6, then arrive around 10. Due to the 3-hour difference between the time zones, the flight is expected to take about 7 hours, including time spent taxiing on runways and waiting to take off. So it says here an important factor in scheduling these flights is the actual airborne flying time from takeoff to touchdown. And that's what the quantitative variable is in this case. All right, it's the actual airborne time, call it, in minutes. And they took this data for flights on, I guess they randomly selected 28 days. Maybe it wasn't randomly selected, but should have been. On 28 days in January 2019. So there's some question about whether it's random or not, but we'll assume random sample. All right, so the question says here, use the data to find a 95% confidence interval for the mean flight time on this route from Boston to San Francisco. Now, the problem, the particular data is actually in an Excel file. You all know how to find these files now in STAT02260. It's called Flight 433. And there's 28 entries. And if I was going to give this to you in a test, what would you do? You simply enter the entries into a list in your calculator, right? And do one variable statistics and find the mean and find the sample mean and sample standard deviation. And that would be it. You'd have X bar, sample mean, S, the sample standard deviation. So either you'll be given the information or you'll calculate it using a calculator. That will be the two choices typically in a test situation. All right. Now, they say that n is 28. It's not large enough for the central limit theorem. But let's assume that the population times are normal. This particular sample doesn't look like it's skewed too badly. So they're saying, okay, we'll use the T. Now, again, don't worry about this sort of testing to see if the T is appropriate or not. Well, you'll never be asked to do that. Just assume that you'll be able to use the T for the sample mean. All right. Anyway, so they give the X bar, according to this, the sample mean is 371.1 minutes is the average time for the 28 flights. And the sample standard deviation is 16.7 minutes. So basically out of those 28 flights, you put it in your calculator, calculate the sample mean, you get 371.1, sample standard deviation 16.7. All right, so you have everything you need here, and they say find a 95% confidence interval, right? So how do you do this? Well, I'm going to write down this information. So I'm going to write down the X bar is 371.1. And again, if you're sitting down and you have some pencil and paper, you can do the same thing. Sample standard deviation 16.7. We want to find a 95% confidence interval. Now, a lot of students in this case here, they make the mistake of using 1.96 for thinking that you're going to use a Z. But in this case, because you're using the sample standard deviation for the mean, estimating the mean, we have to use a T. So please do not use 1.96 in this case, all right? You're going to be using whatever the calculator tells you to use. So, and what is it? And the sample size is 20. Yeah, we need that too. All right, so let's unshare and actually do this problem with the calculator. We're going to do it in a similar way to the way I showed in class, using certain steps that save some time and don't involve much rounding. So you're doing a minimum amount of work when you do this. All right, so I'll clear the screen, and first thing we're gonna do is find that t value, t critical value that we're gonna enter into our margin of error formula, right? It's t times the standard error. That's our margin of error. So we're gonna use inverse t. And again, those with the 83 just follow along. You're gonna be doing this another way. I'll show you on Wednesday about that. Now, if it's a 95% confidence interval, that means the middle area is 95%. We have 2.5% on the left tail, 2.5% on the right tail. Can somebody tell me what area we would put in here to find the positive t? So middle area is 95%. That means the two tails are 2.5% each. So what am I going to put in for the area?
0.975.
That's it. Uh-oh. I'm echoing. Hopefully it won't echo again. All right, so 0.975. And by the way, if you were really, really didn't want to even do that, right? You could actually put a little formula here and do it. Okay. You could do something like just say, you could put 0.95 plus 1/2 times 0.05. You could do something like that if you wanted to. If you really wanted to calculate, do all the work for you. But in this case, I think it's pretty simple. It's just 95% plus 2.5%. So it's 0.975. What now? If the sample size is 28, what are the degrees of freedom we can have here? So anybody can yell out the answer.
27.
27. That's right. 27. And that's all you enter. It's pretty easy. Enter again. And there is your t critical value for the margin of error. Now, once again, you don't have to round at this point. You can simply use all the digits that are being used here. And I'm going to hit the multiplication key, and I'm going to multiply this by the standard error. Now, I'm going to put the standard error in parentheses. You don't have to, but in this case, but it might be useful to keep it straight in your mind because it's a fraction. And what's the numerator? We're going to use what in our numerator? Once again, the mean is 371.1, the standard deviation 16.7, and the sample size 28. So what's going to be our numerator in the standard error? Anybody? Anybody new? Maybe somebody who's
16.7.
16.7. All right. Somehow I'm echoing with you. And then we divide by, so we hit the division key here. And we have to do the square root. So the square root is second, and right above the x squared button is the square root. And what are we going to put inside the square root?
The population.
I'm sorry, Corbin?
The sample size.
Sample size. What is that in this case? Actually, you could see right above this, you could see when I did inverse t, the degrees of freedom is 27. So if you didn't remember, what must be the sample size? It's
28.
28. It's one more than that. That's right. Okay. Now, for those of you who may not know this, notice the arrow's still inside the square root. To get it out of the square root, hit the right arrow key on your calculator. Takes you right out of it, and then you can close the parentheses. Okay? So what you're looking at here is the t critical value times the standard error. This whole thing is going to be your margin of error. Hit enter, and that is your margin of error. Now, you could store it at this point. This makes your life a little easier. So I'm going to store it. Remember, the store button is down here. All right. And I'm going to store it in a letter. I'm going to use A. Hit enter. And so that number, 6.47558 and so forth, is now stored in alpha A. And that's my margin of error. So to find the lower endpoint of the confidence interval, I know my sample mean is 371.1. And I'm going to subtract A, alpha A. There's my lower endpoint. And then the upper endpoint is 371.1 plus A. There's my upper endpoint. And if you round to 3 decimal points, which again, I would like for you guys to do, unless I tell you otherwise, the lower endpoint is 364.624. The upper endpoint is 377.576. And that would be your answer. Okay, so the answer to this question then, in interpretation would be, I'm 95% sure that the population, that the flights, all the flights for this particular United Airlines flight, between, what were the two places again? Was it New York and San Francisco? Whatever it was, is between 364. Let's say I'll ask you to round it to 1 decimal point. So 364.6 minutes and 377.6 minutes. You could say something like that. All right, so that would be an interpretation of the confidence interval. Any questions about that? Pretty much what we did before, except the critical value is t instead of a z, and the standard error looks different, right? It's a different standard error formula for a mean as opposed to a proportion. All right, but it's basically the same formula, same thing. Okay, well, no questions. Let's move on. Go back to the book. Okay. Yeah, they have it all here. All right, anyway, we'll move on. Now, here's the other thing I want to go over today, and then we'll call it a day. It's basically doing the sample size, minimum sample size formula. We were doing that last time for proportions. And it gets derived from, again, the margin of error formula. Now, I think many of you probably didn't like what I did in class where I did a derivation from one to the other. So I will skip that. Just know in general that it's just a rearrangement of the formula. Now, the formula for the margin of error, when we're estimating a population mean, is this formula once again. It's ME, which is margin of error, is equal to T critical value, they call it T star, times the standard error, S, the sample standard deviation divided by the square root of the sample size. Okay. Now, what they're trying to do is solve for n, so there's going to be squaring involved here, but once you do all the algebra, you end up with this formula here, which is nice because everything's inside a parentheses and all of that is just simply squared. Now, here's the problem with using this formula. And maybe if you were, if you saw how the t is derived, you know that it's dependent on degrees of freedom, right? The t, inverse t, depends on degrees of freedom, and the degrees of freedom is the sample size minus 1. And then you're saying, well, wait a minute, I'm trying to find the sample size. How can I find the t if I don't know the sample size, right? Because you're trying to find the sample size. This is before you even have a sample. So there's an issue here. You don't know what to use for t. You don't know what to use for this s, because the sample standard deviation, you haven't even done your sample yet when you're thinking about what your sample size should be. Now, the margin of error, you can figure out what that is. You could just say, I want, all of it to be within 5 or 10, whatever the number might be. So that's fine. Margin of error, you can figure that out up front. So what is the problem? How can you address this? Well, one way of doing this is replace the t, and this is the only time you're going to do this. Replace the t with a z, with the standard normal. So you're going to use inverse normal, and just in this case, so that you can come up with a reasonable estimate for n, the sample size. So in this formula, you can't find t, so you're going to use z, the normal, standard normal value, and you know how to find it with the inverse normal. What are we going to use for s? Well, typically, the problem will give you a estimated population standard deviation. Or maybe there was some similar population that was looked at in the past, and they found that the population standard deviation is this. So you're going to use something that the problem will give you. Another possibility is to use this formula right here. So this is something you may want to pay attention to, because it's possible that you may be asked to use this formula. So how do you find this formula? It says use the range divided by 4. Now, if you remember, the range of a data set is the largest number in the data set minus the smallest number. So a reasonable estimation of the standard deviation of your population. So, for example, if they tell you what the range is for the population, then simply divide it by 4. All right? And that should give you a reasonable estimation of the population standard deviation. So if they don't give you any number to use, but they do tell you the smallest value and the largest value, simply subtract those two to give you the range and divide it by 4, and then replace the s up here with that number. All right, so once again, for this particular problem, replace the t with a z using inverse normal, replace the s with some estimate of the standard deviation. Either they will give you that number, or you use this calculation here, range divided by 4. And then you'll have the margin of error. Something will be given to you about the margin of error. And simply divide all of that and multiply multiply the critical value times the standard deviation in the numerator, divide that by the margin of error, and then square the result. And that should give you the answer. All right? And then, of course, when you get your answer and it has a decimal, no matter how small the decimal is, round up to the next whole number, and that will give you your minimum sample size. And that's how to do this type of problem. So the best way to do this is to do an example, right? We should do this example. And so let's look at this particular one. This is the flight example again. And so we already had a sample, right? There was already a sample of 28 flights from it wasn't New York, it was Boston to San Francisco. And suppose you want to do an additional study later, all right? You want to use some more bigger sample. And suppose you want a 95% confidence interval that you're going to do in the future, all right? And you want to, and you want your margin of error to be 2 minutes, all right? 2 minutes, that's your margin of error, all right? So what does that mean? That means that, that means the length of the interval, the confidence interval that you ultimately get when you run the study is going to be 4, because the margin of error is 2. You're going to subtract 2 to the left endpoint, add 2 to the right endpoint, whatever the sample mean is, and the length of the whole interval is going to be 4, just be double the margin of error. So anyway, that's what it being asked for. Margin of error is 2 minutes. And then they give you, they say 95% confidence interval. Now, in this particular case, you know it's 1.96, right? Because you're using a Z instead of a T. And their Steve is telling you the estimated population standard deviation, 16.7 minutes. All right, so I'm going to write all this down. I'm going to show you with the calculator how to do this. All right, so we have 16.7 and 2. So let's go to the calculator. And again, I'll show you quickly how to do this so there's no issues at all with doing this type of problem. There's the screen. So it's simply going to be a calculation problem. So you get to your main screen, open up a set of parentheses, and in the numerator, you're going to put your 1.96. Now, if you didn't know what the value was, you would do an inverse normal at this point, and actually you could if you wanted to. But since we know the 95% confidence interval, we'll just type in 1.96. And we're going to multiply it by 16.7, which is our estimated population standard deviation. And then we divide by, and we put our margin of error as 2, close the parentheses. Now, before you do anything, now you may want to at this point hit enter and then square, but that is unnecessary since you have used these parentheses. This is why you use parentheses, because you're going to square. There is a square button. It's right here. It's right below the square root. And if you simply click square, notice that it squares that, everything inside the parentheses, and the cursor comes down to the regular level. And if you hit enter, there's your answer. Well, almost your answer, because you have to round up to 268. So originally, the original study had 28 flights, but if you wanted to create a confidence interval with a margin of error of 2, and 95% confidence interval with margin of error of 2, you actually need many more flights, right, in your sample, 268 as opposed to 28. All right, so that's how you do it with your calculator. Pretty simple. And then you'll see the answer. Just round up to the next whole number, and you're done. Any questions about that? How to do a minimum sample size problem here? Okay. No questions. All right. Let me see if there's anything else in the text that would be worthwhile sharing with you. See, there's the answer right there, 268. And the rest of it is just some examples. Does anybody want me to do another example before we leave? Would you like to see another example of a confidence interval and also a minimum sample size problem? Anybody want to see that, or is it pretty clear what to do? It's really up to you.
I would like to.
Yes?
I would like to see it.
Okay. Which one would you like? You want to see both of them?
Yes.
Okay. All right. So let's actually do a word problem. Let's find one that has both of those, probably more later ones. All right. So maybe I'll just pick one each. We'll find one of each type. A simple one. Yeah, let's look at 6.107. It says a study that was introduced in the previous one. We could look at the previous one that was 6.106. It says a study of transgender adults who are seeking gender-affirming surgery examines the age in which they began to transition and the age of their earliest memories of gender dysphoria. Okay. So anyway, 6.107 is referring to that. In the study of 210 adults, that's your sample size, the mean age at which they first remember feeling gender dysphoria was 6.6 years old, with a standard deviation of 3.7 or 3.5 years. Find a 90% confidence interval for the mean age at which transgender people first begin sensing that they are transgender. All right. So it's a pretty good problem. So when I do a problem, I usually write down on a piece of paper all the information I need. I see the sample size is 210, so n is 210. X bar is going to be 6.6, and S, because it's the standard deviations from the sample, it's not from the population, is 3.5. So they give you this information, it's not from a data set. And you need to find the 90% confidence interval that estimates the mean age in which transgender people first begin sensing they are transgender. So let's go ahead and go to the calculator. Clear this out. So when you start out with a problem like this, the first thing that you may want to do is calculate the critical value using inverse t in this case. Now, if you don't have it yet, you will have it on Wednesday if you have the 83 calculator. So again, just follow along. And I'm going to scroll down to inverse t, hit enter. Now, this is a 90% confidence interval, which means if you drew the t distribution with a mean of 0 in the middle, you have the middle area to be 90% with 5% on each tail. So that means the area is going to be the middle area plus the left tail. So it's 90% plus 5% or 0.95. Now the sample size is 210. So the degrees of freedom is 1 less than that, which is 209. Hit enter. And that's your T critical value, 1.65217 and so forth. Now I'm going to multiply that and by the standard error, and I'll again open up a set of parentheses here. And it's going to be the sample standard deviation of 3.5 divided by the square root of the sample size, which is 210. Make sure you use not 209, but 210 here. All right, hit the right arrow key to leave the square root. Close the parentheses. Hit enter, and that's your margin of error. Looks like it's 0.4 pretty much, but we'll use that number. And I'm going to store it in A. So I'll hit the store button, alpha A, hit enter. And now that margin of error is in my alpha of A. And now I'm going to use the mean of 6.6, sample mean of 6.6, subtract the margin of error, which happens to be stored in A. There's my lower endpoint. And the upper end point is going to be 6.6 plus the margin of error. And there's your answer. Now, if you were going to be asked to round it to 1 decimal point, which would be reasonable in this case to do, the answer would be 6.2 to 7, right? If you're rounding to 1 decimal point. So you could say something like you're 90% sure that the average age of that people think that they are transgender is somewhere between 6.2 years and 7 years old. All right. Person who asked for the problem, is that good? Is that straightforward? Good? Yeah. Questions?
No questions.
That's good. All right, good. And does anybody want to see another minimum sample size question, or are you good with that? You're fine with that? Any requests for that? Because the time is pretty much up. I don't want to keep anybody later than they need to be. Everybody good? All right. So that will be it for today. I think, and what we're going to do on Wednesday, we're going to continue in 6.2, and I'll show you the steps of doing a confidence interval there. All right. I'll point out to those of you who came in maybe a little bit late, I'll show to you again on Wednesday the resources. I've got plenty of resources for both 6.1 and 6.2. It's in this week's module in Canvas. There's videos in there that I pre-recorded several years ago that you can listen to again. There's examples in there similar to what I did today, but for all 4 of those sections, or for both sections, but for both confidence intervals and hypothesis tests, all of it's in there. Plus there's some handouts, PDF documents that you can look at also. All right, so there's plenty of things to look at. There's the Wiley Plus videos too. But again, send me questions if you have any questions about your homework. So, anything? Any questions? No? All right, good. So I will see you in person on Wednesday. I should be better, feeling better by then. And that's it for today. So I'll stop the recording. There's no other questions.